This is section 822. We're going to take a look at theorems about complex roots. So we're going to understand the number of real roots and imaginary roots a polynomial function can have, and then we're going to determine the number of real roots a polynomial can have. So they sound similar, but they're slightly different. So how do we determine real roots, or how can we? This is going to be a question that we're going to kind of answer over the next few lessons. But visually, we should be able to get to the point to where we can look at a polynomial and then be able to know how many roots there are going to exist. So just looking at this, I can say that there are going to be 2 real roots, right? Because it crosses the x-axis here and it crosses the x-axis here. 2 real roots. On this graph here, I have 3. 1, 2, and 3. Now we know that a polynomial can also have imaginary roots. So if I shifted both of these graphs up, if I asked that same question, how many real roots are there? And so by shifting that graph up, there are no more real roots, but now it has 2 imaginary roots. This one previously had 3 roots, but when I shifted it up, it only has 1 real root now. Well, where do those other 2 roots go, right? We would categorize them as imaginary roots now. And so just know that the number of roots have a very direct correlation to how our polynomial looks. So when it comes to a polynomial function, the degree that, well, I'm just going to call it n, the highest exponent, that degree tells you how many zeros are going to be in there. And so it could have at most n real zeros, which is the same as n x-intercepts. So the degree, the highest exponent, is how many roots you have, including multiplicity. Now we need to make sure though, with our multiplicity, it's like you count it as many times as your multiplicity. And it's kind of weird, and we're going to see that concept develop a little bit more, but just to kind of give a brief example, this polynomial, because it says 3, my degree is 3, I know that it's going to have a maximum of 3 roots, both real and imaginary. Now this, we don't know how to yet, but that actually factors into this, which means I do have a real 0 or real root of -3, but the multiplicity is 3. So this is saying I need to have 3 zeros, but I only have 1. That's where multiplicity comes in. Even though my 0 is -3, my multiplicity is +3, and so this gets counted 3 times, which is why it can give me that x to the 3rd. So now going back to the same thing here, just remember, this could represent x to the 3rd power, which means there are 3 roots, 1 real, and then the other 2 are going to be imaginary. And the reason why I know it's at least 2 is because remember, all imaginary roots come in conjugate pairs. They come in pairs of 2. Now this leads us to Descartes' rule of signs. Now I do apologize, my neighbor is jackhammering into concrete right next door, and it's kind of loud, so I apologize. What Descartes' rule of sign tells us is possibilities for the number of positive and negative zeros. So what we need to do is we look at the polynomial and we count the number of variations of sign, which means the polynomial itself is changing from positive to negative and negative to positive. Then we take whatever that number is and we start counting down by 2, or an even number, and each of those scenarios are a possibility. You do the same thing with the negative. You plug in a negative for the x value, and you do the same thing. So after you plug in the negative x and you simplify, you count the number of times the sign changes, and then you count down by that even number, and each of those are going to be possibilities. So let's look at this value right here. So we have 2x to the fifth minus 5x squared minus 3x plus 6. And so I want to know the number of positives, zeros, negative zeros, and imaginary zeros. So we count the number of times the sign changes. So here it goes from positive to negative, negative to negative, so nothing, negative to positive, so that's another change. So that means that I have 2, but we start counting down by an even integer, so the 2 scenarios I have is 2 positive zeros and 0 positive zeros. And I can write that in, 2 positive zeros and no positive zeros. Then we can do the next thing for this one. Now, for the negative zeros, I plug in a negative x. Negative zeros, negative x. Positive zeros, positive x. Negative zeros, negative x. Helps you remember. So you plug in that negative x. Now you have to simplify it. And an easier way to do it is like, well, if it's an even number of negatives, well, then it's not going to change because it's still going to be the same value. But if it's an odd number like this, the sign is going to change. So negative 2x to the fifth, negative squared, so it's not going to change. Negative to the first, so negative and negative is a positive. And so now I need to count this. Negative to negative, nothing. Negative to positive, 1. Positive to positive, nothing. So I only have one possible negative zero, or one negative zero there. That's my possibility. And so I can associate with each of those positive zeros that negative zero. Now, they should all add to my degree. So 2 plus 1, now I have 2. So I have to have too many, so that should equal 5. And then in this scenario, that should give me 5 as well. I have to have 4 imaginary zeros. So they should add up to 5. Now, Descartes' rule of signs is limited in the sense that I don't know which possibility is. It could be this possibility. It could be that possibility. I don't know. But I do know at least it's one of those 2 possibilities. So let's look at another one. So counting the variations in sign. So with my function, positive to negative, 1. Negative to positive, positive to negative, negative to positive. So that's 4. Now I'm going to count down by an even integer. So 4, 2, and 0. This is a scenario, this is a scenario, and this is a scenario. And now I have to associate that with the negative zeros. So I plugged in a negative. So negative x, negative x, negative x, negative x. Now I want to simplify it. Negative to an even, nothing changes. Negative to an odd, changes. Negative to an even, nothing changes. Negative to an odd, changes. And that's the same as well. So we count it. Nothing changes, right? There are no variations in sign. The sign doesn't change here. So 0 possible negative zeros. So my scenarios, I could have 4 positive zeros, 2 negative zeros, and 0 positive zeros. So 4, 2, and 0 are my positives, and then negative every time it's going to be 0. So my imaginary zeros in this scenario, I have nothing. In this scenario, I have 2, and in this scenario, I have to have 4 because they all have to equal 4. Now I want you guys to give this one a shot. Use Descartes' rule of signs to do it. Remember, the first, you should be looking at the positive zeros. So counting the number of variations, positive to negative, and negative to negative, so that's only 1. So now we have to do the negative, so we have to plug in negative x. So f of negative x, perfect timing for them to do construction work. It's so good. All right, so now simplifying this, a negative to the 6th power, that's still that. I still have that, and that's still minus 5. So nothing really changed, and so counting this, I get 1. And so you get 1, negative 0. Now my n is 6, which is why that is 6 there. And so I know I have 4 imaginary zeros for this. I have 1 positive 0, I have 1 negative 0, and I have 4 imaginary zeros for this polynomial here. Let's try another one. All right, so getting this down, negative to positive, positive to negative, negative to positive, positive to negative. That gives me 4, 2, and 0 for my possible positive zeros. Now I need to plug in a negative. So now simplifying that, that's going to be negative 7x to the fourth, because I have 4 negatives, so nothing happens. This is going to change, because I have 3 negatives, negative times a negative times a negative times a positive. Here, that's squared, so nothing changes. Negative, negative is a positive. And then that. So counting doesn't change, 1 change, 2 changes. So I have 2 and 0 for my negative possibilities. All right, so let's fill this out. I have 4, 2, and 0 for my positives. Now, for this one, my negative zeros would automatically have to be 0. And for this one, my imaginary zeros would also be 0 because it has to equal 4. Now for 2, I'm going to erase this 0 real quick because for my 2 positives, that can map to 2 negative zeros, right? There's 2 possibilities. And 2 positive zeros could also be mapped to 0, which means 0 imaginary and 2 imaginary. And then my 0 positive zeros could be mapped to 2 negative and 0 negative, which mean I have 2 and 4, because those have to equal 4. So these are, I have 5 different scenarios in how my zeros could be either positive, negative, or imaginary with this polynomial. I don't know which scenario it is yet, but at least it gives me an idea for it. So let's conclude today's lesson. What did we learn today? Well, we talked about a few theorems that allowed us to interpret what the real and imaginary zeros or roots of a polynomial are. And so it's the degree that's the most important. And the degree tells us how many zeros are in a polynomial. If you add up the number of imaginary, if you add up the number of real, including multiplicity, that tells us, that'll give us what the degree of the polynomial is. And then Descartes' rule of signs tells us how many positive, how many negative, and then by default, how many imaginary zeros are possible, like the different scenarios within that polynomial. So this does conclude our lesson. If you have any other questions, please leave them in the comments.